Hello everyone, Ashley here. The whole purpose of this online tutorial is because we couldn't run the class on Friday 13th. Hence, we've tried to kind of see other means that we could use to deliver the lecture. So hopefully you can get to listen to this, and I hope as well that the quality is fine. So basically, today's lecture was going to be on the second part of time series. But before we do this, briefly a recap of last week, which is here. So last week, what we saw was, if I quickly, well, first of all, we explained the meaning of time series, and we looked at different plots and different types where we have the trend, increasing and decreasing, and stationary. And what else can I say? Right, the periods here, for example, you start with 0, 1, 2, 3, and 4. So the period's 4. Another way of finding the period is you just ask yourself the question, how many quarters in a year? And the answer is 4. Anyway, this is what we did last time, and we kind of talk a little bit about this. So today's class is basically more on this and uh, some extension on the chapter. So I'm not going to talk about these right now. That was for last week, but we're going to come back to these in today's session as well. Anyway, so that was last week. Right. So today is, like I've said, we're continuing where we stopped, and that's what we did last week. We looked at the nature of time series and its components. So nature would be increasing trend, decreasing trend, stationary, and components, if you remember, would be the trend, the seasonality, uh, the residual and cyclical, and so on and so forth. What we want to do today is look at appropriate methods of forecasting for a data set, and also talk about why we want to do this. Second one is to check the strength of a particular method by examining the residuals. If you remember the meaning of residuals, it would be the errors that we have between the true value and the forecasted value. Third one is to decide whether the forecast is reliable, and I don't know how to remove this, but that's fine. And finally, uh, we have to make a decision based on our forecast. So that's what we saw. That's what we are going to do today. Right. So this is. I wasn't too sure whether to go through the slides or to go through the booklet. So I'll keep switching between these two. So I think now is the right time to move to the booklet. So this is week 20, and basically this is what we've just been discussing. Now let's look at one example we saw last week, something like this. And if I ask you what type of trend do we have, you would say this is fairly stationary, and that's because it keeps fluctuating between 41 to 58. And if I were to put a straight line across these points, the straight line would be somewhere kind of horizontal. And basically the whole point here is, if the line is going to be horizontal or fairly horizontal, then what scope do I have to do any forecast? It's going to be quite boring. It's going to be quite limited. And that's the first example we're going to look at. Now, one example that we're looking at here is a case where the mean is about is about 50. And how do I get the mean? By taking the price. If these are share prices, then I'll take all these share prices and add and divide by, well, it looks like around 100 values here, and hence I'll get um, around 50. Now you could, if you remember your Excel sheet, that's not the one. if you remember the Excel lab work, you could do something similar. I'm just trying to find where it is. You could do something similar and discover these things yourself. So, for example, if I have this, then I can easily do the mean here, right? So you know what I'm writing here. You know what all these functions mean, and I could just select this. And there you go, 50.01648, which I think I just saw. There you go. Right, so this is one way of finding the mean, and clearly I could find the variance and then the standard deviation and prove that these results are correct. Anyway, so like I've said, the bottom line here is it's pretty much a little bit limited for me to do forecast, just because there's hardly any trend here, in the sense that it's easier if the trend was upward or downward, but here it's kind of horizontal or kind of stationary, hardly ever moving. Now that's the whole point of it, because when we have situations like this, it's hard to do forecast. But remember, at the end of the day, the game is about forecasting, and what we want to do is, let's say, answer a few questions. For example, how well or how poorly our forecast is or would be, and so on. So that's basically the idea, and let me show what I'm doing here. So there you go. Right, right. So what we can do is to find errors, and there are several ways of finding errors. So, for example, here, and I do hope you've tried this in your lab session. One way to get a graph here would be to select the data. You might want to leave these two here. It's up to you. It's kind of handy. So you go to insert, you go to scatter. You can choose any one of them. It doesn't quite make such a big difference. It's whatever you fancy. Let's keep it simple. Let's take this one, because it hopefully looks familiar. You've just seen that on the PDF file. And then I right click on any of the dots. I add trend line. By default, it's linear, and it gives me the equation the of the trend line here. And if you do remember your chapter of regression and correlation, I can then find the forecast value if I use this equation. So for example, for me to find the forecast value, I can just say equal to, and that's the equation here. So bracket, I like my brackets, as you know, so minus 0.0029 multiplied by x, close bracket, plus 50.164, and that would give me the forecast when x equal to 1. So that's the true value here, and this is the forecast which I can get if I use this particular equation here. And if I drag this down, I'll get the forecast value for the different x's that I have. Now clearly, as you can see, there's an error or a residual. You can call it residual, doesn't matter. And uh, the, the calculation here is, you take the true value, you minus the forecast value, and you get the error in your forecast. So this is the true value minus the forecast value, and for x equal to 1 for the first coordinate, this is the error that happens. So I don't know if you can see it properly here. Maybe I should remove the grid. All right. So if I kind of make this bigger, as you can see, the dotted line is here and the true value is here. So when x equal to 1, as you can see here, this is the true value, 44.012003, well, right? And the forecasted value is around here. So there is a gap of 6.14. The minus just tells me that the forecast is way above, is above the true value, hence an error of minus, which means above, right? And I can do this for the whole set, and hence I can find the errors for each of the x's here. Good. Now, one thing you can do is just find the average of these errors. So if I were to find the average of the errors of the residual, then this is what I would get. And it's minute. It's very, very close to zero. Now the question is, was it expected? Or is this strange? And so on. Now, if I tell someone that the error in my forecast is almost zero, then the person would tell me that, okay, you're quite accurate in your forecast because the error is zero. Whereas here clearly I can see that I've made major errors. There are lots of errors between my true value and my forecasted value. And these are the numbers, these are the errors. Minus means the forecast is above the true value, plus means the forecast is under the true value. So really, I mean, we have some weird, strange, big numbers here. That's a difference of 3 point something. And if I move up, let's say any massive difference, there you go, this is 4, and I can move up and so on, and there's a 7 here for x equal to 6. I can have an error of 7 pounds or whatever it is, which means that's my true value, that's my estimated value. There is a difference of 7.23 pounds between these two. So it's not really common sense to say that the error on an average is zero, whereas I am indeed getting it. So as you can see, there is some limitations here, some discrepancy in terms of interpretation. If I have to repeat, if I give someone this information here that my average error is zero or very close to zero, it sounds good, it sounds perfect. It means that my forecast is pretty much accurate, when actually even the graph is showing me that that's not the case. We have, for every point, we have quite a gap, quite some error. So that's the whole point of today's session. And this is how we find error, which I've just done on Excel. Actual value, the true value minus the forecast. You know how to get the forecast value. Just take x equal to 1, 2, 3, 4, and so on, and substitute that in the equation of the line, and you'd get the forecast. Do the difference, the subtraction here, and you'll end up with the error. So, right, that's what I'm saying. The whole point is that sometimes giving error or an average error might be misleading because of obvious limitations like the one you've just seen. So before we move on, when error is greater than zero, when we have a positive error, let's just see. When error is positive, let's take this number or this number. Let's take this one. When error is positive, all it means here is that my forecasted value is less than my actual value, right? So when error is positive, it means that the actual value is uh, larger than the forecast. If it's positive, did I make a mistake here? Yep, that's fine. So if it's positive, it means that the actual is larger than the forecast. Let's just double check this again. If it's positive, it means actual is larger than the forecast. There you go. Actual is here, forecast is here, and hence I have a positive error. There's nothing to learn by heart here. It's just common sense, and you can easily understand what's happening. So similarly, if it's negative, then the reverse is happening. If it's negative here, then it means, for example, this one, clearly the actual value is less than the forecast, hence a negative error. There you go. So if it's negative, error is negative, it means actual value is smaller than the forecast, and so on, right? And this is known as an overestimate. The forecast is higher than the actual, hence I overestimated it, and so on. When there's zero error, it means that the actual value is equal to the forecast, right? So that's what I'm saying. If you do the mean, it's pretty much misleading because we end up uh, sorry, I'm just trying to find my key here. Uh, we end up with zero. My mean error, my average error is zero. It sounds like I did a pretty much good forecast based on the data that I had. And you saw yourself that's not the case here. Right. So, okay. Right. So that's one way of finding, that's one method to find a numerical value which can summarize error, which is the mean error, the one that we just did. So we do the errors. So we find the errors for each one of them, and then we find the mean, and we get the mean error, which is, oh, come on, which is here, mean error, the one that we've just done. Now we have other means, and we could do this one as well, the absolute error, or the mean and the mean absolute error. So AE and MAE. So absolute error, I think if you're familiar with this term, is to convert everything into positive, and then add them and so on, divide by the number of elements, the number of observations that I had, and I will get the mean. So I could do it here quickly for you. Just don't want to waste too much time here. So I'll take the absolute error, which is I'll convert all these numbers A, B, S, absolute, right? And there you go. So I convert all negative values into positive. So absolute error means I convert all the errors negative into positive. That's the formula here. And if you drag it, obviously positive stays positive. And there you go. So positive stayed positive, negative became positive, and then now I can find the mean. So I'll just so not to waste time, I'll just drag this. So there you go. The average of this column here, E2 to E103, that's 103. The first number was E2, and I have a slightly more plausible summary of errors compared obviously to this one, which had its limitation, which kind of didn't make sense. So now I have something slightly better. So that this one was average. That one was mean error. It's in the notes. This one was absolute mean error. Oh, sorry, we call it mean absolute error rather. So mean absolute error. There you go. Right. So this one is mean error. And we have other ways of finding of calculating a summary for errors. The next one could be, let's square the errors. I mean, you should ask yourself the question here, why did we convert negative to positive? What's the idea behind this? So the idea is errors or errors, whether it's an overestimate or underestimate. When we have plus and minus, we are being very specific. We want the audience to know that there is over and under depending on the plus and minus. Whereas when I say absolute, I'm kind of ignoring whether it's over or underestimate. All I'm saying is there are errors. So let's convert everything to positive. So please do think about the limitations now using mean absolute error. Now, one step that we can do to progress from here would be, why should we get rid of the minus? Why not square the numbers and the minus will get rid by itself, but it makes mathematical sense to square it. Whereas by just ignoring the minus sign, it doesn't quite make sense here. We can't just ignore a minus sign. Whereas if we square it, mathematically it would make sense. So here we'll square the errors and then we'll find the mean of those numbers. So for example, I could square the errors, square the errors. Remember the initial errors, which means this number to the square. There you go. And drag down. That's fine. And then I could now find the mean, and I would get something like 9.5, I think, for MSE, the mean squared error. The mean squared error. Right? So again, it's just a progression on this one, maybe an improvement, which is even an improvement on that one. So we are kind of progressing by understanding the limitations of each and every one and trying to improve on the way we are doing our mathematical calculation. Now again, you should ask yourself, we just squared the numbers. I mean, why do we just square? What's so important about square? Well, the importance is we don't ignore the minus does get converted to a plus sign by a proper mathematical method. But then another question comes in. I've just taken a number and I've squared it, and I'm saying, okay, let's not consider the initial number, let's consider the square. So somewhere something is going wrong, and hence I can say, okay, let's balance it, and instead of using mean square error, I'm going to use root mean square error, which means why not find the root now? That is, find the root of the mean of the square of the errors. So all I'm going to do here is I'm going to do equal to SQRT, open bracket, and just do this, and I'm going to get a new number. So basically all I'm saying here is I squared the numbers to get this. Let's balance it out and put a square root, SQRT, and I should get a slightly more valid or plausible or common sense answer or summary for my errors. So as you can see, we have a range of ways to summarize errors, and here we have four, and I do hope you understood the calculation here. So that's basically ways to to work out the errors. There you go. I think that these are the numbers we got. 3.55, right. So let's take this one, 3.085. Yeah, to two decimal places, it's correct. So anyway, um, that's different ways of finding errors. I'm going to move on now, and I think these are for practice purpose, and you can read a little bit here. I think the main point was for you to kind of understood the several ways where we can find errors. Right. Okay. Now moving on, one of the things that we might like to do, I'm going to still stay on the PDF here, and I'm going to talk about the residual plots here. Right. So One of the things I would like you to practice as well is to plot the errors that you get, and it's a good thing because you might see something quite interesting. For example, you might see whether errors are focused. Um, Things that you expect when you plot the errors, which I'm going to do for you in a few minutes, would be that the errors should be centered around zero, and that's the first thing, and so on. And the errors should have a constant variance, and so on. I mean, I'll let you read this. They should be independent, which means there should not be any trend in the error. They shouldn't follow any particular path. They should be scattered all over the place. That's what I mean. These two are kind of connected, and basically, they should follow a normal distribution. That's probably something that I can explain later. But for the time being, if we plot the error graph, we will end up with this. So if I come back to my Excel, I don't think I need this one. I'm not too sure what this is. Don't save. Right, let's stick with this one. So for example, if I want to plot the errors, which is this, that's the x-axis, against this. Oops, do you see? I don't know what I've done. Let's see now. My mistake. Oh, it's not focal. Sorry. Errors. There you go. Right. So this is what I get. I don't think I need this graph for the time being. Let me just put that somewhere else. So all I've done now is I've plotted this x-axis against the y-axis, which is now known as errors. So I'm plotting the error graph here, as you can see. So these would be the errors, positive and negatives are here. So as you can see, it's kind of scattered around this particular line here. There is there will be quite a few dots above and a few dots underneath, which makes it kind of the mean being zero, and there's no specific path, there's no specific trend. It's scattered all over the place. That's good news, right? You do want this to be scattered all over the place. This is what I mean by um, independent. So just think about it. If it's scattered, it means my errors cannot be is not following a specific trend, and it's all over the place, and that's what I do want. If it was following a trend, then it means that I could focus the error. If the errors were following, let's say, some type of curve, then I know what will happen after a few steps. They will still carrying on that particular trend. So I don't want this to happen. I don't want my error to be dependent on the x-axis. It has to be scattered all over the place. So there you go, independent. All right. What do you think about this one? Do you think that the mean is zero here? Do you think if I draw a line on the zero axis, well, on the horizontal axis here, do you think it we have same number of dots, well, not same but almost the same than under? I'm not too sure about this. So here it looks like the middle point, the midpoint is about -2. If I draw a line here, I feel that we have enough points under the line here and above compared to the 0 point. So this is just to tell you that we might have some trouble here. Okay. Right, so this is what we've seen last week. I don't think I want to waste too much time here. This is an upward trend, and hence you can dump a line. You know how to do this. I've just done that in Excel. You can do this to get a line and do forecast and so on. And here the errors are, uh, I would say the errors now are following a trend. Even the errors are going upward. That's not really good news. Uh, this is perfect. It's scattered all over the place. Whereas this one, it seems to me that my errors go bigger and bigger and bigger when we do some forecasting here. There you go. The errors mean is 2154.2 when actually I would like my error to be around 0. Right. The rest is quite easy. We covered that last week. The trend, that is, get the trend line in Excel and so on, and then you can do focus. I think you've seen what I did earlier on Excel. So I'm going to move on to the next part of the lecture, which is so we've seen these things, which is so all this has been covered last week. Uh, some summary here. Yeah, we saw that last week, and. Even this graph. Now this is not really much in the syllabus here. This is not a linear forecast. As you can see, we have exponential here. Not really in our syllabus, but what I can say here is when you do Excel and add trend line and so on, by default it's linear. That's just one option, and we have several. For your syllabus, we'll keep it linear for the time being, and but we have more. We could have quadratic, cubic, exponential, as you can see here, and so on and so forth. That's just to show you that we do have other things uh, beside linear. Right, so all this was seen last week where we have oh, maybe now it's not. Now this is new, so let me go back to the slides here. I don't know where it is now. Right, so there you go. So let's see what we can do here. These are the errors calculation. We've discussed that on the PDF file. Right, so there you go. So I would think, yeah. So what we want to do now is is one step that uh, we can we can perform, and I think I mentioned that last week. And the whole idea here is to flatten my graph. So the method that I mentioned last week was moving average. So moving average is quite an interesting thing. If I can quickly show you some graphs later, let me just show you a graph first. Let's move out of this. There you go. The blue graph is the graph for the original data, and the red graph, which we haven't discussed yet, has been obtained by using a method called moving averages. And as you can see, the red graph is slightly flatter than the blue graph. And that's the whole point. We do want to make it flatter and flatter and flatter. Let's see if we have anything else that's slightly flatter and more, and it gets flatter again. So I'm not going to discuss why right now, but the whole point, the reason is here. So that's what we're going to discuss. So let me go back to the slide for moving averages. So the method to soften our graph is known as the moving average method. Right, it's quite easy. So this is one example we saw last week: sales of barrels in 1,000, and the timeline is given here. The x-axis, where I would call this 1, 2, 3, 4, 5, 6, and so on. And my first question will be, what would be the period? So you can choose two peaks, this one and that one, or two troughs, this one and that one. Let's focus on the peaks, this one and that one, and count and see the period. So you start from here, you're going to stop here, but you start with 0, 1, 2, and 3. So the period is 3. Now I can use a moving average with the period 3. There you go. the period 3. So it's not always an arbitrary number. It's based on the periods of your graph, right? So let's look at how we proceed with moving average. So this is the x-axis. This is the y true value, the exact value of sales. Remember, in thousands. And I don't want this. I want to use moving average to come up with new set of values which I can then plot. And the reason I want to do this moving average is because moving average helps me deal with periodicity. So I can soften my curve, which means I can make it flatter and get rid of periods. So there you go. So two things I want you to focus on. The first one being the true values. The second one is n equal to 3. So how do I proceed? I'm going to find first step. This is my answer here. My answer will be in the last row. I don't know how to move this. There you go. So first step is to find the moving total using n equal to 3. So how I'm going to get this? I'm going to take the first three values, first, second, and third, and I'm going to do the total. So 35 plus 15 is 50. 50 plus 42 is 92. That would be the total, and I'm going to write it exactly in the middle. So the three values, the middle is here, so I'm going to write 93 here. Right, let's see how we can get it. There you go. The next total would be, first of all, I took these three values, I found the total. Now I take the next three values. Just don't make the mistake of taking these three. You started with these three, so the next will be 1, 2, and 3. These three cells, and the total will be here. So 15 plus 42 is 57. 57 plus 36 is 93, I think. And I would put this in the middle. So this is the three cells. I would put the total here. Right. Ignore these two for the time being, and I'm pretty sure you know what just happened here. So you can see how you got 93. Remember, the final row, the final set of cells is what I need, and that's the average. So for me to get the average now, I will do 92, the total, divided by 3. That's because I took three numbers. That's because the period is 3, and I'm going to get this number instead. And how do I get 31? 93 divided by 3. This one, think about it. I will take 42 plus 36 plus 19 is going to come here, the sum, the total, and I'm going to divide by 3, and I'm going to put it here. So let's see. There you go. And so on and so forth. This is how I get the moving total first, step 1, and step 2, the moving average. So right now, instead of using these 1, 2, 3, instead of using these 12 numbers, I'm going to use these new set of values here. Now, what's the advantage? The advantage is that you're getting rid of the periodicity, the peaks and the troughs. That's the whole point of moving average. You're going to make your graph flatter. But what's the disadvantage? The disadvantage is you started with 12 points, and here you are using only 10 points. So you've just lost two values. It's obvious here why, because this cell is empty and that cell is empty, right? So think of the advantages of using the true value and advantages of moving average, and also the disadvantage of moving average, which means that you have less data to work with. And there you go. So there you go. I've just put the summary here. Moving average of y, as you noticed earlier, this is empty, this is blank, and this is blank, and that's gonna give me the pink curve, which is flatter than the blue curve, blue set of points. And clearly in the test, what you might expect is for you to draw this pink well, I won't say line, I'll just keep it as curve here. This pink curve, it's not straight. It's from this point to that point to that point. So 30.7 is here, 31 is here, 32.3. So please don't give me a straight line. Second, make sure you start on the second x value, because there you go. On the first x, it's going to be blank. So I don't want the pink dot to start above the first x. It has, in this case, it has to start just above the second value of x here. There you go. And the last value also is blank, which means above this there should not be any pink dot. And that's the my 40.3, which is here. Right, so this is something that you might expect for the test. The blue graph will be given to you, and you will be asked to randomly uh, plot the moving average. You're not expected to be very accurate. Maybe it's worth 1 point, but what we want to see is that your dots on the pink is in the middle of those blue dots. That's one. That's the first thing. Second, do not start on the first above the first x value, no above the last x value. Common sense, because it's blank and it's blank here. You started with 12 blue dots. You now have 10 pink dots. Right. So this is one case of 3-point moving average. Clearly, you have some values missing on the red line, on the red curve. Oh, sorry, on the red graph, for obvious reason, and so on. Maybe there's a mistake here. Maybe there's a mistake here. I don't think it's a 3-point moving average. I think it's a 4-point moving average here. Right? So yeah, 1, 2, 3 on the fourth point. 1, 2, 3. Yeah, it is a 4-point moving average. It's a small mistake here that you can correct, and so on. Right? It goes. We can keep doing this. And this is a 9-point moving average. So think of how many data you'd lose here. You're taking the first 9 values, you're getting the total, you're dividing by 9 to get the average. So the first value will fall on the 5th point. The middle point of 9 first values is the 5th point. So you're losing the first 4 and probably the last 4 as well. At 17-point moving average, right? So you're considering the first 17 points, and you're going to do the sum, the total, and you divide by 17. That number will fall on the 9th value. Think about it, the 9th value. So you're losing the first 8 the first 8 points here, and the first value will be on the 9th here, and so on. Right. We could also do moving average here, where we have an upward trend, and again the whole point is to make it flatter. And this is a 4-point moving average, so clearly you lose a few values at the beginning, and at the end the red one is a forecast, and so on. Right, now the summary is, I'm pretty sure you will get to try this in the lab. The summary is moving average is not a suitable method for forecasting data with a trend upward or downward. What you want to do is usually focus on periods where we have periodicity, and then use moving average to just remove the periodicity and make it flatter. So this is one conclusion that you might want to remember. Now it becomes a little bit more tedious now, so I would need your attention. You might want to pause the video tutorial now and take a break and come back later, because it might get a little bit too much right now, as from here. Okay, so what we want to do is, we want to use a couple of models, first additive then multiplicative, and try to see what happens. So additive, the word itself is telling me we're going to add, and I will take my time to explain this, and I do hope you understand what this is. What you are used to especially in the chapter of correlation, is um, is to draw a line across the points, and there's a trend upward or downward usually. That's the trend here. That's the trend here, right? So that's the value that I will get using y equal to a plus bx. Just here. What I'm telling you right now is usually when we have seasonal elements, we can improve on just using a plus bx. We can consider the season. I think we should consider the season, and we should consider the residual here. So for me to get a better forecast, I can use trend, the line, plus season plus residual, right? So um, how do I know I can use an additive model? Remember first, let's see that if there's season here. Yes, we have seasonal periods here. So 0, 1, 2, 3, 4. Here n equal to 4. How do I know we can use an additive model? It's quite easy. Uh, I don't know if I have to move quickly to the multiplicative model just to compare the methods or the approach, but just bear with me. The point is I can use additive model when let's show the next slide. You can take a ruler and yeah, you can take a ruler or you can draw the upward trend, and then you can calculate the distance between the true value and the forecast value. For a peak, we might just use this for the trough as well, doesn't matter. So when I can't see really which one is which. So this is 2010 Q1, Q2, Q3, Q4. There you go. That's 2010 Q4. That's the true value. You can find the estimated value and find the difference here. You can do the same here. You can do the same here. If those values, those errors are similar, that's when you know you can use a additive model. That's one way of doing it. Another way of doing it is take your ruler, place it on the dots. It's not going to be straight, but roughly, if you place a ruler here and a ruler on the peaks and on the troughs, you will see that the two lines are straight. So kind of draw a rough line here across the peaks and a rough line here across the trough. You will see that the difference, the gap between the two lines is almost the same. Hence, you can use an additive model, right? So that's another way of doing it. There you go. So there you go, right? So you will have almost similar errors, and hence you would know that this is an additive model. Let me quickly show you what happens for a multiplicative model. So let me quickly go to some other slide. Right, for a multiplicative model, it's this is a multiplicative model. How do I know this? If I try to place a ruler here and here, you will see that the two lines are not really parallel, and they are kind of like this, diverging or converging, right? So see the difference between the direction of the lines here for a multiplicative model. Here in this case, they're diverging, they're not really parallel. Whereas for an additive model, you you will have to identify which model to use. So additive or multiplicative. So for an additive model, you will have lines which are kind of parallel, right? Okay, so let's come back to the additive model here. Right, okay, so this is what we have. So we've discussed this. All right, so let's look at this example here. Like I said, it might get slightly a bit tedious what I can expect for the test is this is given to me, this is given to me, and this is given to, well, to me means to you in the test, and this is the true sales, true value of y. Now clearly you cannot have this. By all means you can plot your graph with the x-axis being all these texts, but it will make more sense if you assign a number to these, hence number 1, 2, 3, 4, 5, 6, 7, and so on, 12. And if I ask you a question, what would be the meaning of 13? That would be the next step here, which is January to April 2014, right? So you should assign numbers uh, on the x-axis instead of these, and you know why, because these x values will be substituted in the line y equal to a plus bx, so you want your x to be numbers instead of text. So that's why we have a new set of x-axis instead of this one. By all means you can plot both. Right, so let's move on. Right, so if I decide to plot uh, this against this, I'll let you do this yourself. I don't know if you have this in the Excel sheet. Um, we don't, but I'll let you do this yourself so you can practice a little bit. Um, I don't know if I should do it. It might take a long time. So there you go. X. Ter values, I think we had. Right. So these are the ter values. Did we have ter values? Right. Yeah, 12 values here, and these would be my true value, my sales. Guys, it might take a long time for me to do this. I'm pretty sure you can do it yourself, so I'll let you practice a little bit. Anyway, so you can add your trend line, which is right click, add trend line, linear, write the equation, and you will end up with this. Now this is the difference here. Earlier in our earlier classes I would call this y equal to a plus bx. Now nothing's changed. All I'm saying here is let's give it a proper name. That's the trend. So instead of y, I'm calling it t. That's for you not to get confused with the y here. For you not to get confused with this y. So right now all I'm doing is this t here. Remember that would have been enough for the chapter correlation and regression. And um, earlier we used to call it y. Now because of some progress that we've made because of seasonal elements, I'm just focusing on this one and I'm calling it t because we have something else called y. So all I'm doing here is this, right? So that's why I call it t, right? So there you go. So I hope you know how to get this. And then if I substitute x equal to 1 here, I will get the estimated value. That would have been enough for our chapter regression and correlation to get the estimate for x equal to 1, x equal to 2, x equal to 3. Right, let's move on now. So this would be a true value, that's the estimated value using only my equation of the straight line, and I've called it t, but that's not enough, right? So remember why it's not enough now, because in this case we have seasonal components which I want to consider when I do forecast. Right, okay. Right, so this is our graph, and I'm gonna, it's an upward trend. There you go, and we have seasons where n equal to 0, 1, 2, 3 here, and we want to estimate, we want to come up with a better forecast. Now let's see what's happening here. I've decided to consider a peak. You could have considered a trough. You should consider a trough eventually. So I've considered the peak, and I will consider peaks rather. So this is one peak, that's another peak, and I will find the difference, the error, the residual here, and here, and here, and yeah, this looks like a peak as well, and here. So there you go. I will find this. So how do I get this difference? It's my true value and minus my trend value, and I would get the error, the difference here. So there you go. Right. So this is where we are. I'll take my true value, I'll subtract the trend, and it will give me the season plus the residual. Now, one thing I should start with is uh, an assumption. My assumption is that the residual is 0. Let's say we didn't leave any mistake. I hope you remember the residual component last week. Residual component means mistake that can happen when we measure. So let's say there was no mistake. That's one assumption, which means this equation now simplifies to y minus t equal to s plus 0, hence s equal to y minus t. So for me to find the seasonality at every dots, all I have to do is take my true value, subtract my trend value, and there you go. That's my true value, that's my trend value, the forecast, and if I do the subtraction, and for obvious reason, there you go, that's the obvious reason, when I do the subtraction I will find the seasonality. So there you go, and I end up with this, right? Now remember the whole point. Now the whole point is for me to consider S for future forecast, right? So uh, I'm gonna, sorry, I'm so sorry about the noise. My son is next to me and he's kind of being noisy. Anyway, so right, okay. Let's sorry, I'm a bit distracted right now. Yeah, let's focus on the second one, the second trimester, right? So I'm going to consider this. This is just an example. I could have considered the first trimester, January to April, and so on. I'm just focusing on one of them. So I'm going to take May to August, and this one, and this one. So my season for May to August is this much, and this, and this, and this. So if I want to do an improved forecast for the future, not only should I consider trend, I should consider the seasonality which is happening between May and August. So there you go. I'm going to consider these four May to August periods, and I'm going to find their average. So how do we interpret this value? We can interpret that the seasonality which is happening between May and August on an average is about minus 14.8336. I'll let you think about the meaning of minus here, right? We've discussed that earlier today. So on an average, the seasonality between May and August is minus 14.8336. Understand how we got this value on this slide here. So for me to do future forecast, not only do I need to know the trend, I can also implement this seasonality component and get a better forecast for the future, right? So this is how it works. We know the trend, we just calculate the seasonal component S. We're going to combine both to do what? To come up with a better forecast. So there you go. This is my equation of the trend. What if I take x equal to 14, which doesn't exist in my set of data? My set of data was between 1 and 12, so clearly 14 is sometime in the future, which is May to August 2014. Now, in the chapter correlation and regression, I would have just substituted 14 here. I would have got the trend 44.98. Here, I'm just saying stop. I've found another way to improve on this by focusing on the season component of May and August, and let's implement it. So there you go. I know the seasonal component for May and August is this much as well, and hence an improved estimate would be the trend value 44.9838 plus the seasonal component, which I just got as an average, plus R, which I said earlier will assume to be 0, and hence in our chapter correlation regression we would have stopped here, and now we've just improved on our forecast. Remember why? Because of the seasonal component, which I'm now considering, and then come up with a better forecast. So in our chapter correlation and regression we would have stopped here, whereas in this we are improving on our prediction, and we will have a better accurate answer only because there was seasonal components here. There you go. That was for additive model, where remember we considered we assume R to be 0. Now let's move on to multiplicative model. Remember as well we use multiplicative, so the equation is here. Instead of plus we will have multiplication. Now clearly if you think about it, I cannot assume R to be 0 because then the whole thing here will be 0. So I will assume R to be 1. Hence y equal to t plus s, t times s times 1, and hence y equal to t times s. Right? So, and I discussed this earlier. We knew it's a multiplicative model because the difference here is converging, unlike earlier, which was almost parallel for a additive model. Now, for a multiplicative model, you can see that the lines are kind of diverging. There you go. So here is our formula. I will assume R equal to 1. Remember, I want to isolate S, so I'm gonna move T and T on the left side. There you go. Y divided by T will give me S times R. I will assume R to be 1, which means the next line you will see it's Y divided by T equal to S. There you go. S equal to Y divided by T. So for me to get the seasonal component, I will take my true value, I will divide by my trend value, and I will get the season for that particular period. Right. So uh, this is one example, and I hope you understand why these two are empty, because for me to get the trend, remember I could have used regression, I could use moving average. Both methods are fine, uh, depending on the situation that I have. So earlier in additive model I've used regression T. Here I've decided to use moving average to come up with this. For me to get this is S. For me to get the season here, the seasonal component, I will do Y divided by T. That's my Y, that's my T, and hence I can end up with the seasonal component for each particular period, which I can consider then to predict in a more accurate way. There you go. So, for example, the second seasonal component here, the second quarter. Let's move up. The second quarter here, it's blank. I'm not gonna consider it. I'm gonna consider this one and this one and this one. I can find an average which is 0.9099, which I will then consider to have a better prediction. Right, so similar to earlier, I will find the trend. In this case, I did moving average instead of the line. I've a focus on the seasonal component, which is 0.9099, and I'm going to combine them to predict in an accurate way, in a more accurate way. There you go. Right, so Let's move on here. Right. So let's combine them. Y, Y equal to T from moving average. And I'm looking at the second quarter here, prediction. Multiply by S 0.9099, multiply by 1, that's our assumption. And instead of 6 to 8, I will have a better prediction for the second quarter. Hence, I think there's a mistake here. It shouldn't be 2002. I can't remember what it was. I think it's 2012. I don't know. I mean, I'm not going to go back and check. But instead of having this as a forecast, I've combined the seasonal component with my trend. Remember, the trend here is not through a straight line, but instead through moving average. I can do that, no problem, and I end up with a more accurate forecast just because we had some seasonal component. There you go. With the multiplicative model. Okay, we didn't show you here. There you go. Right now, I'll let you read this. This is the kind of comparing multiplicative and additive model. I'll let you read this. Um, yeah, there's nothing much to explain. You can read yourself, and that's the end of week 20, I think, of our module. I hope to record the next one, which is week 21 soon, but and upload both somewhere so that you can listen and come prepared for the next class. If there's any question, you can ask me. I would expect some questions because it's kind of tough to do this without facing you, but come up with the questions in the class and we can discuss more on this chapter. Thank you for listening.